Have you ever pondered the emotional conflict between a furious star and its planet? A young planet, near a red dwarf star, changes in astounding ways each time it orbits the star. When NASA's Hubble telescope first observed it, the planet's atmosphere seemed protected. However, about 18 months later, Hubble discovered that the star's strong energy waves, driven by stellar winds, were pulling the planet's hydrogen atmosphere away. The planet's mysterious atmosphere presents a puzzle, undergoing dramatic shifts from one orbit to the next. But why is this red dwarf star unleashing its high-energy fury on its own planet? Join us in this video as we explore NASA's astonishing observations and uncover the marvelous mystery of a furious star. The Hubble telescope, orbiting Earth, can detect when a distant planet passes between its star and Earth by capturing the star's light. This movement causes the star to appear slightly dimmer for a brief moment, signaling that something caused the temporary dimming. This method is how scientists first discovered the planet OMIC B in 2020. However, for that initial discovery, it was NASA's Spitzer and TESS telescopes that spotted it first. Now, though, Hubble has made its own OMIC system discovery. Scientists observed something more intriguing than just changes in starlight during a typical transit. By closely examining the light waves, they found the dimming of starlight from OMIC B was much deeper than expected, extending beyond the planet itself. It was not solely due to the planet passing in front of its star. OMIC B orbits its host star OMIC every 8.46 days, at a remarkably close distance of just 6 million miles, 9.6 million kilometers, about 1/10 of the gap between Mercury and our Sun. It lies only 32 light-years from Earth. This star, classified as a red dwarf, is notable for its extreme nature and is one of the youngest known stars, with an age of approximately 23 million years. Despite its proximity to the star, the planet experiences significant fluctuations in atmospheric loss during each orbit. Red dwarfs, the dominant stellar objects in our Milky Way galaxy, are known for their intense magnetic fields and substantial stellar flares. These stars can release energy surpassing our Sun's eruptions by up to 10 times. It's 23 million years old, which is extremely young. Essentially a toddler star, said Key Rockcliffe, the lead author of a study on the new Hubble findings and an exoplanet researcher at Dartmouth College. Astronomers are excited because OMIC B provides a glimpse into the youthful, tantrum-like years of a red dwarf, one of the most common types of stars in the Milky Way. Surprisingly, the cause of this immense activity is the material escaping from the planet's atmosphere, slowly fading into space. This remarkable finding reveals a phenomenon called atmospheric evaporation, driven by the red dwarf's powerful, high-energy outbursts. Hubble's data showed that these strong energy blasts, referred to as stellar winds, are responsible for the changes. The star's intense radiation strips the planet's atmosphere, creating a turbulent environment. Scientists believe the changes in OMIC B's vanishing atmosphere might be due to its unpredictable red dwarf star. Perhaps a major energy burst from the star turned the escaping hydrogen invisible to light, or maybe the strong winds from the star affect how the planet's atmosphere drifts away, making it appear and disappear at different moments. What's fascinating about OMIC B's atmosphere is its inconsistency. Sometimes, the star appears restless, affecting the planet, while at other times, it's calm and causes no changes. Rockcliffe and her team hypothesized that the planet's gravitational pull caused some of its material to separate from its core, leading to this escape. She described it as the material being strategically swept away, offering us an enchanting glimpse into the intricate dance of this distant cosmic pair. I remember when I first made the light curve of this planet with our Hubble data and saw that the transit happened well before the predicted transit of the planet, Rockcliffe said. I immediately thought, well, I definitely made a mistake. However, no matter how many times I reanalyzed the data using different methods, the result was the same. When atmospheric evaporation was first observed, it was in planets known as hot Jupiters. These are some of the most extraordinary exoplanets in the universe, essentially hotter versions of Jupiter because they orbit very close to their stars, making them incredibly warm. However, what we haven't often found are planets like OMIC B with such dramatic atmospheric behavior. To give a clearer picture, Rockcliffe explains that using such limited data to understand the whole process is like extrapolating the daily experiences of the working class from the life of a wealthy individual. Atmospheric escape, she noted, is one of the most influential evolutionary processes for most exoplanets. This work could help scientists unravel the nature of worlds beyond our solar system, where they reside, and perhaps even guide us toward understanding their habitability. Red dwarf stars, the most common in the Milky Way, are believed to host many planets. Yet, the rapid and unexpected changes we observe in these stars pose a puzzling question for astronomers. Rockcliffe emphasized, there's a big mystery about how exoplanets might be losing their atmospheres. When we study these distant planets, one big question stands out. What's causing their atmospheres to vanish? Is it the intense radiation from their star, or could it be heat from the planet's own hot, young core? It's crucial to note that we've observed a planet's atmosphere escaping ahead of the planet itself. What's even more curious about the atmospheric changes in OMIC B is their unpredictability. It's as if the star has mood swings, sometimes agitated and affecting the planet, while at other times, calm and undisturbed. My perspective or intuition tells me this behavior is intricately linked to the atmosphere's interaction with OMIC stellar winds, Rockcliffe said. OMIC stellar winds might be causing turbulence as they interact with the atmosphere, leading to this time-variable burping of hydrogen gas. She's also contemplating the planet's distant future based on Hubble's observations. While these ideas are still in their early stages, a couple of intriguing possibilities stand out. If the planet loses its entire atmosphere and is stripped to its core, it could resemble Mercury. However, if it retains some of its lower atmosphere, it could evolve into a world with unique atmospheric conditions, perhaps with dense clouds or even an entirely different climate system. OMIC B and its fiery host remind us of the countless wonders and mysteries awaiting us beyond our cosmic neighborhood. Could the extreme behavior of red dwarf stars like OMIC B affect the habitability of their planets, including the potential for life to emerge? As we continue exploring the vastness of space, the mysteries surrounding exoplanets and their stars remain a focal point of modern astronomy. The study of exoplanets, worlds outside our solar system, has surged over the past few decades, revealing an astonishing array of peculiar and unexpected planets. While the discovery of planets orbiting stars like our Sun has garnered much attention, the most fascinating and often misunderstood planets are those orbiting red dwarf stars, such as OMIC B. The properties. Red dwarf stars, being the most common type of star in the Milky Way galaxy, make up about 70 to 80% of the stars in our universe. These stars are smaller, cooler, and less luminous than our Sun but have incredibly long lifespans, lasting tens to hundreds of billions of years. Despite their abundance, red dwarfs present unique challenges for scientists trying to understand how planets in their habitable zones could support life. Unlike the Sun, which is relatively stable, red dwarfs are known for their turbulent behavior. They are characterized by powerful solar flares and intense magnetic activity. These flares release enormous amounts of radiation and energetic particles, which can have significant effects on planets orbiting too close to their stars. For planets like OMIC B, located at a dangerously close distance to its star, the effects are particularly dramatic. The planet's atmosphere is subjected to constant bombardment from stellar winds and radiation, leading to atmospheric loss. This makes it increasingly difficult for such planets to retain stable environments that might support life. Interestingly, OMIC B's situation offers scientists a unique opportunity to study atmospheric evaporation and its long-term effects on planetary evolution. By examining the interactions between the planet's atmosphere and its host star, researchers can better understand how exoplanets evolve in extreme conditions. This research also raises important questions about habitability. Red dwarfs are known to host many planets within their habitable zones, but their volatile nature could make these zones far less hospitable than previously thought. The constant radiation and stellar flares could strip away atmospheres or create environments too harsh for life to develop or survive. Rockcliffe and her team aim to continue studying OMIC B and its fiery host star, using tools like the Hubble Telescope and other upcoming missions. They hope to uncover more clues about the processes shaping exoplanets and their potential for habitability. These findings could have profound implications for our understanding of the universe and the possibility of life beyond Earth. The case of OMIC B underscores the incredible complexity of planetary systems and the dynamic relationships between stars and their planets. It also highlights the need for continued exploration and study of exoplanets, particularly those orbiting red dwarf stars, as they make up the majority of planetary systems in the galaxy. As technology advances and new telescopes like the James Webb Space Telescope continue to deliver unprecedented data, the mysteries surrounding exoplanets like OMIC B may become clearer. For now, OMIC B serves as a fascinating reminder of the intricate and often chaotic interplay between stars and their planets, offering glimpses into the extraordinary diversity of worlds beyond our solar system. The distance to its red Bantam parent star, these flares, and heavenly breezes represent a genuine danger to air trustworthiness. As a matter of fact, researchers have seen that such stars can strip away the atmospheres of neighboring planets, a peculiarity that could have significant ramifications for the planet's capacity to hold liquid water and, likewise, support life. The challenge for cosmologists is understanding the specific processes that lead to this atmospheric erosion and how it varies from one planet to another. While planets closer to red dwarfs are more vulnerable to these effects, the interplay of factors such as a planet size, magnetic field, and atmospheric composition can all influence the degree to which a planet's atmosphere is stripped away. For instance, planets with strong magnetic fields might be better equipped to shield themselves from the harsh radiation emitted by their stars, while those lacking such protection are more prone to atmospheric loss. One of the significant puzzles that scientists face is determining whether a planet can retain its atmosphere over long periods. Some models suggest that planets orbiting red dwarfs could experience a runaway greenhouse effect, where the radiation from the star continuously heats the planet's atmosphere, preventing the formation of a stable climate. This process could lead to a Venus-like scenario, where the planet becomes so hot that any potential for liquid water is lost, and any chances for life are extinguished. Other planets might undergo a more gradual process of atmospheric escape, where the outer layers of the atmosphere are slowly eroded by stellar winds over billions of years. Regardless, the fate of these planets is inherently tied to the behavior of their host stars. Despite the apparent challenges that red dwarfs pose to the habitability of planets in their vicinity, scientists are not entirely dismissive of the possibility that life could exist in these systems. Some researchers have suggested that even if planets in close orbit around red dwarfs lose their atmospheres, they might still harbor subsurface environments where life could potentially flourish. These underground habitats could be shielded from the harmful effects of stellar radiation, offering a refuge for microbial life or, in rare cases, more complex organisms. Moreover, the discovery of extremophiles on Earth, organisms that thrive in extreme conditions, such as deep ocean vents or acidic hot springs, has led scientists to broaden their definition of what constitutes a habitable environment. In some ways, red dwarf stars might even offer opportunities for life to develop in ways we have not yet imagined. For example, the habitable zone around a red dwarf star, where conditions are suitable for liquid water to exist, is much closer to the star than it is for sun-like stars. This means that planets in the habitable zone of red dwarfs are likely tidally locked, meaning one side of the planet always faces the star, while the other remains in perpetual darkness. While this presents challenges for the planet's climate, it also creates unique conditions, such as the possibility of vast, stable regions of liquid water near the planet's terminator line, the boundary between the day and night sides. These areas could be prime candidates for supporting life and might be much more stable than the rapidly changing conditions on the planet's sun-facing or dark side. Furthermore, the frequent stellar flares emitted by red dwarfs could provide a different kind of energy source for life forms. On Earth, solar flares are associated with space weather events, but these phenomena are much more common and intense around red dwarfs. Some scientists speculate that the energetic radiation from these flares could potentially drive chemical reactions beneficial to life, serving as a catalyst for complex biochemistry in ways we do not yet fully understand. As astronomers continue to observe red dwarf systems with increasingly sophisticated tools, new insights are emerging about the potential for life in these distant worlds. Advances in telescope technology, such as the launch of the James Webb Space Telescope, JWST, are providing unprecedented views of exoplanets in the habitable zones of red dwarfs. The JWST's ability to analyze the composition of distant atmospheres and detect the presence of chemicals such as methane, carbon dioxide, and oxygen could help scientists determine whether these planets have the right conditions for life. If signs of life are detected, it would be a groundbreaking discovery, potentially opening the door to a new era in our search for extraterrestrial life. Meanwhile, researchers are focused on studying the behavior of red dwarf stars in even greater detail. By understanding how these stars interact with their planets, scientists hope to unlock the secrets of planetary formation and evolution. For example, By studying the magnetic fields of red dwarfs and how they influence planetary atmospheres, researchers can gain insights into the conditions necessary for life to thrive on exoplanets. The study of planets like OMIC B provides a unique opportunity to observe the effects of stellar winds and radiation on a planet's atmosphere in real time, offering valuable data that can be applied to other planetary systems. As we continue to look beyond our own solar system, the potential for discovering habitable planets around red dwarfs is an exciting prospect. While the harsh conditions posed by these stars might limit the chances for life in some cases, they may also reveal entirely new forms of life and environments that we have yet to imagine. The exploration of red dwarfs and their planets is not only advancing our understanding of the universe but also expanding the boundaries of what we know about the potential for life in the cosmos. Whether these distant worlds can support life remains to be seen, but the journey of discovery is just beginning. The mission to understand the relationship between red dwarf stars and their planets is a crucial part of modern astrophysical research. As technology continues to advance, we can expect to learn more about the complex and sometimes volatile interactions between these stars and their planets. The story of planets like OMIC B, with its dramatic atmospheric changes, is just one example of the many mysteries that await us in the far reaches of space. While these findings might challenge our understanding of what makes a planet habitable, they also remind us of the immense possibilities that exist in the vast universe.